Hey there. Let's talk about accepting command line arguments in a pure assembly program written for x86-64 aka AMD YASM assembly. On Linux. Anyway, so there are going to be a lot of topics that I sort of mention in this video that are not actually covered in this video. So if you feel yourself getting lost, like for example, if you don't know how to program in assembly in the first place, if you don't know what command line arguments are, if you don't know the terminal, things like that, you probably want to check out my previous videos because they will be explained in detail. For now, I'm just going to assume you know how to do all this basic stuff, and the only thing that I need to show you is how to write a program in YASM assembly that can grab your command line arguments. So, just to do a quick recap of what I'm even talking about, if we have a program named Echo, we can launch it with no arguments. It doesn't do anything, but we can give it some arguments. We can say hello, and then we can say goodbye, and that's two arguments that I'm giving to Echo. Echo will grab onto the arguments it was given. It's actually going to receive three arguments, the index 0 argument being the name of itself, its own program, and then the next two arguments being the stuff that I typed after the program. But you can see that it somehow figured out how to grab these two arguments as strings and print them, right? So imagine you have an assembly program and you want the user to be able to launch your program and add arguments at the end of the command line and have your program behave in some certain way according to what the user wants. The question then becomes, how do you access those arguments? It's a little bit easier in GCC. Look at my other video that I posted about the topic for GCC linked assembly programs. It's a little bit easier. You pretty much just look at RDI and RSI to get your argc and your character pointer array. When you're dealing with pure assembly, though, the GCC libraries don't bundle up the command line arguments in a really convenient way for you. You've got to look for them elsewhere. It's honestly not that much harder. It's just feels a little weird, I think, at least for me. I was hoping to see the arguments in a register, and I did not. But anyway, so here's my program. Again, this is not an assembly programming video. If you need to know how to program assembly, see my other videos. For now, I'm just going to quickly go over it. I've got my data section in YASM. I am printing out a couple of strings, I have a couple of strings defined. I'm saying like the module has started. I'm going to begin printing arguments. I have some system call codes so that I can write to standard output, and so that I can exit the program. This is pure assembly, so we don't actually return from main. We just get jumped into, and then we call exit normally. And then here's the standard output pipe. Again, another video covers that. And then I've got the exit success code. Again, another video covers that. But basically, exiting 0 is usually what you do for success. Then I've got the text section, which holds all my assembly instructions. And this is my entry point. We don't really need to push and pop these registers because we're just going to exit the program when we're done. It's totally fine. We would need to preserve callee saved registers if we were jumping into a main function, or if this was a different function that was being jumped into. But we're not, so we don't have to. Anyway, here's my entry point, the underscore start for a pure assembly program. And then I'm going to grab the incoming arguments. When you're linking with GCC, which we're not doing here in this video, then the arguments come in very easily. They just come in. argc shows up in RDI, and argc comes into RDI, and the character pointer array comes in as RSI. So you can imagine in GCC, this would be integer main, and then integer argc character pointer array argv, right? Hopefully you've done this in a higher level language so you have a better idea of what I'm talking about. If not, I guess that's okay. It will still allow you to grab, even if you don't understand this in C++. So argc is actually the stack pointer. The stack pointer register, RSP, always tells you, where the top of the stack is. Like, what's the last piece of data that we actually have sitting on the stack. So that's going to be the count of arguments. argc is always going to be the stack pointer. So if you dereference the stack pointer register, then what you're doing is, the stack pointer register actually points to memory locations within the stack. So if the memory location that it's looking at is where argc is stored, then you dereference it with the brackets and you'll actually get argc. So right away, I'm just going to steal argc off the top of the stack. And this is a good idea to do right away, because if you start doing other stuff, you might end up modifying the stack, especially if you start calling functions and things like that. And these pieces of information will be lost, or they'll be a lot harder to find. So right away, I'm just going to say argc goes directly into R12, and I have a little comment reminder for myself at the top saying R12 is now argc. Same thing for R13. I'm going to say that's a pointer to my character pointer array. I talked about this in depth on my other video where we talked about GCC command line arguments to an assembly program. But basically, if you look at argv right here, it's not just a pointer and it's not just an array. It's a pointer to an array. And if you recall in higher level languages, or just, I guess, anything, an array itself is a pointer, because argv, the symbol, let's say we were in a higher level language, argv can only point to one thing. So it's going to point to the very beginning of your array, if that makes sense. But the beginning of your array is not going to be one string, like one argument that the user gave you, because the user could give you many arguments. Instead, it's an array of pointers. So it's a character pointer array, meaning argv is a pointer to a pointer. The first item in any array is what is pointed to by the symbol. So like imagine if we had, just for the sake of argument, imagine if we had an integer array. Let's say we had like 500 integers in like a C++ program. So the symbol A is what I'm trying to say. The symbol A is really a pointer that points to the first integer in that array. And then later, of course, you can dereference that pointer with some sort of an index to get the index 5 integer or the 6th integer, right? So the symbol is both the array and a pointer to the first item. Or I guess you could say it's both a pointer to the array and a pointer to the first item, because it's kind of the same thing. So that means if we grab argv, then we'll be grabbing a pointer. If we then dereference that pointer, it would tell us where another pointer is, and then that other pointer would be would point to a string representing the first argument. So we'll explain that more as I do this loop. I'm gonna show you some code that actually loops through all the arguments. Anyway, the thing about where to find that argv is it's just the next pointer, or I guess it's the next item that the stack holds. So remember I told you that RSP, when this function comes in, RSP is a pointer to wherever we're looking, what memory location the top of the stack is. So if we dereference that, we get argc. Well, we just need to go find the next previous item in the stack and then dereference that so that we can get the first pointer, or argv, you know, the first pointer to a pointer, or the first double pointer in your array of pointer to pointers. Why am I doing +8? This might actually make sense as is, but it's important to understand that when you add stuff to the stack, you're actually decreasing the memory locations that you are pointing to. So like if I increase a stack, this is not a stack video, there's other videos that I have for that. If we add something to the top of a stack, you imagine the stack growing visually in a vertical direction, like it's growing up, right? But inside of the computer, the memory locations are actually going down. So keep that in mind. That means if we're looking at the stack pointer and we're adding 8, what it's saying is that we're looking back into memory that was already added for the stack. So that's like if we grew the stack, that would be subtracting from the memory location. So like looking further up in the stack would be subtracting from the memory location, because the stack grows upward in the abstract, but downward in memory locations. So that means if we add 8, that means we're going in the other direction. We're looking downward into the stack. So what that means is that the top 2 items on the stack are first argc, and then second, that first pointer, you know, the argv argument. And that's how we access it with +8. Why is it a +8 instead of plus something else? Because all pointers on 64-bit systems are 64-bit integers. And 64-bit integers are 8 bytes. If we're talking about 8 bytes, if we're talking about 8 bits per byte. So this is just how you access it. What about this other thing going on here? What's this LEA instruction? Usually you see a move instruction, right? So we basically want to look at the stack pointer, but look one level lower, and each item on the stack is also going to be 8 bytes. We want to look one item lower on the stack, and then we want to dereference it, but we don't want to dereference and store the dereferenced value. We still want to grab the actual pointer. The thing is, I shouldn't have said dereference in the first place. These are dereferencing brackets, right? So like up here on line 46, when you put brackets around RSP, it dereferences whatever value RSP holds. So therefore, when you put brackets around this, you kind of expect that you're going to be dereferencing, right? But we don't want to dereference. We just want the original address that it's showing us. So the problem with this is that when we say RSP plus 8, we can't actually do a mathematical formula unless we're inside of brackets, which means we can't do them in a move instruction without accidentally dereferencing and losing a pointer to the actual array of pointers. If we dereference like this, we would just end up with, a pointer to one string. So the way around this is, instead of using the move instruction, we use the LEA instruction. The LEA instruction allows us to put a formula inside of brackets so that the assembler won't get confused, but then it won't put the dereferenced value into R13. It'll just put the actual value of whatever we see with that formula, meaning it'll give us the memory location of the item sitting one under the top of the stack. Trust me on this. At this point, R13 is now the memory location of the item sitting one underneath the top of the stack. And then we can dereference that later in order to look at all of our arguments. So the next part of our code is just going to print an intro message. So there's like this intro string up here, hello. And I'm basically going to call a custom function that I made to just sort of print another thing saying, we're about to begin printing. Don't worry about this code right here. This is not the point of the video. I just made a custom function that just kind of helped me print. Don't worry about that. The real meat of this video is that we're going to loop through all arguments and just print every single argument that the user provided. So you can imagine this is maybe the top of a while loop here. Notice how, oh, I forgot to replace main with start. I had another version of this program that used main. So let's just pretend we have, this is called the main loop instead of the main functions loop. Anyway, so main loop initialize. First thing I'm going to do is I'm going to initialize the loop by saying we're looking at index 0. Okay, no problem. So we're looking at index 0. We want to do that. We want to look at all the arguments. We want to look at index 0 and index 1 and index 2, and we just want to keep going until we're out of arguments. Remember that we also have the number of arguments coming from argc now sitting in R12. So that means if we have a counter that starts at 0 with R14 and then we know how many arguments there are in R12, we should be able to know when the loop stops. So just a reminder that, the loops here, the arrays here are 0-based indexed or 0 index based, which means, for example, if we have 3 arguments here, if we include the original program, that's 3 arguments, but the array of arguments is going to have indexes 0 and 1 and 2. Which means the last valid index is going to be 2 or the size minus 1. Think about that. If you have 5 arguments, the last index that is valid is going to be 4, size minus 1, because it's 0-based. So we can use that logic to figure out if we're done. So we start off with an index of 0 here, and then at the top of the loop, I'm just going to quickly ask, are we done? How do we know if we're done? We compare the current index we're looking at with the count, and we say, if the current index we're looking at is greater than or equal to the count, then we know we're already done. We don't need to look at any more indexes. Why am I saying is the index greater than or equal to the count? Because remember, if we have 5 arguments, then the last valid index is 4. Therefore, if we find ourselves looking at index 5, we know we're already done. 5 is equal to or greater than 5, but 4 is not equal to or greater than 5. So that's why I'm using this logic here. I'm saying, if we're done, then jump to the done label, basically. What's the done label? It's main loop done. All it really does is it says goodbye, and then it just exits the program with a system call. Again, I have other videos that explain system calls and all that stuff. So if we're done, we we jump down to the done area, but if not, then execution will fall through to this next loop, or sorry, this next label, which is not necessarily, we don't really need a label there, but I like to put it there just to help myself remember this is what it looks like in terms of a while loop. You know, I have like, here's the top of the while loop, here's the little comparison part of the while loop, here's the body, like the opening braces of the while loop, and then here's sort of like the closing braces. I just like to do that. But anyway, after we decided that we are not done and we drop through to the next actual instruction, we're just going to print the next argument. So what's the next argument? We will dereference R13. Remember up here, we took the second item sitting like, you know, one under the top of the stack, and we just stuck it into R13. So this is, R13 is now the address of the second item on the stack. If we dereference it, then that's going to give us a pointer to our, it's going to give us a pointer to the first item, to the first string, I should say, to the first string. The string of the first argument. So if we dereference, let me say this one more time just to make sure that I'm clear on this. The second item, the item right under the top of the stack, that's going to be a pointer to the first argument string. So if we just simply dereference R13, then we're basically telling RDI, here's a pointer to the string that we want to print. Okay, so then I just call my helper function to print that string to standard output, no problem. And then we have to figure out, like, how do we increment to go to the next string? So on the stack, I think I might have been unclear earlier because GCC does it in a different way, but on the stack, every item underneath the top of the stack is another pointer. It's part of the original argv array. It's another pointer to a different string. So basically, if I increase R14 here, then I'm increasing the index counter. That'll help us eventually terminate. But notice how here I'm adding 8 to R13. Remember, R13 is the second item, the item right under the top of the stack. And if I dereference that, then I now have a pointer to the first argument string. If I want to go one lower into the stack, then I just add 8 to that register's value. Because again, remember, the stack grows downward in memory. So if I increase the value, then I'm sort of like going through previous items that were put into the stack. So imagine the stack here, it's got like, argc sitting on top, and then underneath argc, it's got a pointer to the first argument, and then under that in the stack, it's got a pointer to the second argument, and then under that in the stack, it's got a pointer to the third argument, then under that, it's got a pointer to the next argument, and so forth. So every time we want to go to the next argument's pointer, the next argument's string pointer, we just add 8 to that R13 register, which was originally just pointing at the first string. So again, why 8? Because pointers are 64-bit integers, therefore they are 8 bytes. So I'm just literally increasing the index by 1, and then I'm moving that register R13 to point to the next pointer. That way, next time I dereference it up here on line 70, I'll be dereferencing the next string. And these strings don't need to be contiguous. They could be located anywhere. It's the stack that is contiguous, but it's just full of pointers to other strings. Or sorry, it's full of, if we dereference the stack pointer at any point, then we will get the address of a string. So then we will get a pointer to a string. This double pointer stuff, sometimes I get tongue-tied. Okay, so when we're done printing and incrementing, then we just jump to the top of the loop. And then finally, when we're done, well, we're done. Let me draw this out for you because I think the way I'm explaining it might be a little bit unclear. So I just want to make sure that I'm being totally clear on this. Okay, so I've got my little annotator here, and you can imagine here's a stack, and it visually grows up. We can imagine that every time we add an item to the stack, it grows up. Like if you wanted to take a 5, stick it on top of the stack, well, then it would end up on the top of the stack, right? No problem. Oh, maybe this needs to be bigger because of my pen size. Let's do it like that. What the heck happened? I lost the whole desktop. There we go. So we have this and this and this and this. And so there's probably some kind of a value sitting on top of the stack. When we started the program, RSP is a register that just has the memory location of the top of the stack, the most recently added item. We know that this was actually argc. So if we dereferenced RSP, that'll go to wherever argc is and get it. So we can basically say that argc is sitting on the top of the stack. So, we dereference our RSP, which holds a memory location to this place in memory, but at that place in memory, we just had an integer stored, an 8-byte integer. Okay, cool. So then the next lowest, I guess the next highest item or the next lower item is argv at index 0, which is the same thing as just saying argv. Remember, a pointer to the array is really a pointer to the first item. The next lower item is argv at index 1, and so forth. So we can just keep doing this. We can keep going lower and lower and lower on the stack by adding 8 to R13, because remember, R13 originally pointed, to this item right here. I'll say like R13 maybe starts off pointing to the first argument, because that's the way we have it set up. So every time the loop iterates, if we dereference R13, then we're getting a pointer to a string, which is going to be the current argument. And then when we add 8 bytes to R13, we're really just moving it down to the next pointer that we can dereference. Hopefully that was a little bit more clear than what I said before. Or maybe you're just a visual learner. It's a good idea to try to explain things in many different ways. But long story short, we're going down, down, down further in the stack to get more arguments, and we're just printing them. And so now that we've explained it all, we should be able to just run the program. So I'm going to do clear and make run. And under the hood, let me just show you real fast what I've got inside of my makefile. Under the hood, when we do make run, you don't need to know about makefiles. I have a video that explains all of this, don't worry. But, you don't need to know it to understand this video, but you probably do need to know it. Notice how when I call the executable, which in this case is just referred to as a variable named bin, I give it some arguments. I give it just some strings. First arg, second arg, third arg, fourth arg. So that's the same thing as if I typed echo, first arg, second arg, third arg, fourth arg, right? That's what echo is doing. So in the makefile, I'm just giving it those arguments. And then our program now is looping through all of the arguments. It knows when to stop because we grabbed argc, and it knows where those strings are located because the pointers to those strings are just sitting on the stack. So if we deref twice, we're doing a double dereference, a pointer to a pointer. At least we could say R13 is a pointer to a pointer, but the actual values sitting inside the stack are just pointers to strings. So let's just do this in a slightly different way, just so you can believe me here a little bit more. I'll do clear, and then I'll say main, because that's the name of the program that I compiled. You can imagine this could be named something else. And I'll just put hello, you are super cool now. So I'm giving it 1, 2, 3, 4, 5 arguments in addition to main. So it should print 6 things. Main, hello, you are super cool now. So notice how it prints main, hello, you are super cool now. All right, that's pretty much everything that I wanted to show you for the pure assembly version of grabbing command line arguments. Thank you so much for listening. It's a little late for me. The sun's starting to come up. I've got to go and eat a bunch of cookies. So I hope you learned some stuff, and I hope you had a little bit of fun. Thank you so much for watching this video. I will see you in the next one. Happy studying and coding and all that stuff. Hey everybody. Thanks for watching this video again. From the bottom of my heart, I really appreciate it. I do hope you did learn something and have some fun. If you could do me a small little favor, could you please subscribe and follow this channel or these videos or whatever it is you do on the current social media website that you're looking at right now. It would really mean the world to me, and it'll help make more videos and grow this community. So we'll be able to do more videos, longer videos, better videos, or just I'll be able to keep making videos in general. So please do me a kindness and subscribe. You know, sometimes I'm sleeping in the middle of the night and I just wake up because I know somebody subscribed or followed. It just wakes me up and I get filled with joy. That's exactly what happens every single time. So you could do it as a nice favor to me, or you could troll me if you want to just wake me up in the middle of the night. Just subscribe, and then I'll just wake up. I promise that's what will happen. Also, if you look at the middle of the screen right now, you should see a QR code which you can scan in order to go to the website, which I think is also named somewhere at the bottom of this video. And it'll take you to my main website where you can just kind of like see all the videos I published and the services and tutorials and things that I offer and all that good stuff. And if you have a suggestion for clarifications or errata or just future videos that you want to see, please leave a comment. Or if you just want to say, hey, what's up? What's going on? You know, just send me a comment, whatever. I also wake up for those in the middle of the night. I wake up in a cold sweat and I'm like, it would really mean the world to me. I would really appreciate it. So again, thank you so much for watching this video, and enjoy the cool music as I fade into the darkness which is coming for us all.